Hello, I'm Ben Jordan and I'm going to talk about our paper Coreset Spectral Clustering that is joint work of Gregory Schwartzman, Peter McGregor and Hurston. The goal of graph clustering is to find densely connected communities that are highly connected within themselves but not across each other. This problem appears again and again in the wild, clustering social networks, identifying cell types in the brain, or understanding language model embedding spaces. Spectral clustering is an algorithm for solving such a problem. If you've not come across spectral clustering, here's how it works. We start with the adjacency and degree matrices. The adjacency matrix tells us which nodes are similar to each other, and the diagonal degree matrix tells us the sum of these similarities for each node. The first step is to construct the Laplacian matrix. Then we embed all the nodes into the bottom k eigenvectors of the Laplacian, where k is the number of clusters. Finding all k eigenvectors is typically the slowest part. Finally, we run k-means or this embedding space. This gives us the output partition. Our motivation is primarily speed. The reason you may not have heard about spectral clustering before is that historically it has struggled to scale to large datasets with many clusters. Recent work has sped up spectral clustering using powerful approximation techniques. Sparsification carefully constructs a re-weighted subsample of the edges. Another technique shows that we can get away with using log k eigenvectors instead of k. The question we had was, can we get away with using fewer nodes? The goal of this paper is to speed up spectral clustering using fewer nodes. To achieve our goal, we're going to borrow a technique from weighted kernel k-means. These algorithms may seem fundamentally different, however there is a strong link which we will exploit. The kernel k-means problem is essentially the Euclidean k-means problem in a Hilbert space, where we compute distances using the kernel trick given a kernel function measuring similarity. This is obviously more general than the Euclidean setting because our data points can be anything so long as we have a way to measure similarity. On the left is a visualization of this Hilbert space and what good cluster centers might look like. As you might expect, the objective of weighted kernel k-means problem is almost identical to the Euclidean case. As you can see, as we move our candidate centers around, the objective is lowest when the centers are near the centroids of each cluster. The tools we are interested in are called coresets. A coreset for kernel k-means is a re-weighted subsample of the data points such that the objective of any set of centers on the original data is preserved on the re-weighted subsample. Remarkably, we have algorithms that return coresets whose size depends only on the number of centers. To give a more visual description, we can see that as the centers move around, the objective on the coreset never strays far from the original. So what is the connection? Well, the algorithm for spectral clustering can be derived by considering a relaxed version of the normalized cut problem. It turns out that we've known about an equivalence between weighted kernel k-means and a slightly modified version of normalized cut since 2004, but to the best of our knowledge, nobody has exploited it as we do. Using simple transformations, we can map degree and adjacency matrices from the normalized cut problem into kernel and weight matrices for the kernel k-means problem, and vice versa. This connection gives us a very natural way of applying coresets for spectral clustering. Start by translating the input graph to kernel space using the equivalence. Then we compute a coreset of the kernel problem. Then translate this coreset back into graph space. There we can perform spectral clustering on the coreset graph. This is very fast because the coreset can be tiny. Then we translate the cluster partition in graph space into centroids in kernel space. Finally, we label the rest of the nodes in kernel space. Because we run spectral clustering only on the coreset graph, we get all the benefits of coreset kernel k-means without having to run Lloyd's algorithm in kernel space. We provide two theoretical results. The first shows that our algorithm achieves an O alpha approximation given an alpha approximation spectral clustering algorithm for the coreset graph. The constant only depends on the coreset guarantee. Our second result is a faster version of the state-of-the-art coreset construction algorithm for sparse kernels. We improve the running time from O tilde nk to O tilde n times the minimum of k in D average, where D average is the average number of non-zero entries in each row of the kernel matrix. In our experiments, we show that coreset spectral clustering produces significantly better clusters than coreset kernel k-means, and when we apply an existing method for speeding up spectral clustering, it is also faster. One of the reasons kernel k-means isn't often used is because it gets stuck in local minima, and this seems to only become more severe as the kernel matrix gets sparser. Looking at the ARI and normalized cut plots, we can see that kernel k-means struggles even with large coreset sizes. If you want to use our algorithm for yourself, all you need to do is pip install Coreset SC and follow this example or the one on GitHub. Thanks for listening.